linked lists. So what we're going to do is we're going to write our own linked list. We're not going to use built-in linked lists because that's not what the cool kids do. They write their own. So we're going to say issue with arrays. So as we've already noticed, so we can say arrays are fast, but we've also noticed here that arrays are memory inefficient. And from our perspective, it's that we had to make them the max size they will ever be before we can, well, make them the max size that will ever be, and then fill them up completely, and then overwrite. With new data as we get it. So that's been our limiting factor in our array list, right? Or our array adapter rather, is that we have to create these 1,000 bucket arrays and fill them up with fake data in order to make the thing work. Okay? So we want to look an alternative to this. So while arrays are relatively fast and they're memory inefficient, linked lists, these guys are relatively slow, but they are memory efficient. All right, and let's look at a visual difference between these two guys. All right, so if I'm making an array and I say something like int array AR is equal to a new int array size 4, something like that. Anytime I use the new keyword, new memory is being created. Now, this guy is actually something called a pointer. So this variable AR points to a place in memory. So I'm just going to pretend like this place in memory is 316, 320, 324, 328. I just pretended like the new keyword gave us the memory address 316. All right, this is bucket 0, bucket 1, bucket 2, bucket 3 in our array. So if I say something like AR at bucket 2 is equal to 7, what we mean to do is put a 7 right here, right? Put a 7 at bucket 2 in our array. Now, the reason arrays are fast is because this line right here, AR at bucket 2 equals 7, actually means this. Go to the base address AR, add to it 2 times the size of the type, so in this case an int. So that is equal to, so AR has a base address of 316. We're going to add to that 2 times the size of an int. Size of ints are 32 bits or 4 bytes. So 2 times 4 is 8. 316 plus 8 is 324. That's where bucket 2 lives. So we get to various buckets of an array under the hood by mathematically starting from a base address, then jumping forward a integer size step. So I need to take 2 integer size jumps to get to bucket 2. But we can calculate exactly where that lives in memory and just go right to memory address 324 to put it in there. So arrays require something contiguous memory. That is memory right next to each other. So when we request memory for an array, and we say, give me enough memory to hold this many four of these guys, it's going to go out and try to find a 16-byte chunk of memory somewhere on your computer so that it can give you all of those bytes right next to each other. That's contiguous, memory right next to each other. Arrays are fast because the memory is right next to each other because it's contiguous. Arrays are memory inefficient because when you build an array, it's taking up that plot of land permanently, and if you need more space, the real life example with this, with like a house. Let's say you have a house and your house is all built, just got built, and you decide, you know what, I really want to add a deck, and I want to add a deck onto this house. In real life, as long as the money's there, you add a deck, right? In array speak, you don't. What you do is you go find another plot of land that's a little bit bigger than the current plot of land. You copy your house over to that new plot of land. Then you build your deck on the slightly bigger extra plot of land that you have. And then you burn down the old house. Okay, now you want to put a swing set in the front yard? Do it again. Okay, you need to. So what have we done in our current kind of ghetto solution for our array adapters? We just built a big old house. I don't know how many decks I'm going to put out there, but I got room for 1,000. Right? Okay, I got room for 1,000. Yet I'm living in a Maytag box. It's a Las Vegas studio apartment is what it is. But point is, we have lots of wiggle room for extra stuff because we built it on that much land. So we took up a whole bunch of computer memory, even though we've only had 3 or 4 credit cards or loyalty programs built in there, right? Okay. Now, linked lists, on the other hand, let me just drag. Oop. A linked list, I'm going to steal this kind of this look here. Okay, so when I build a linked list, let me drag this over to the side here. So let's say I have a linked list, LL is equal to a new linked list. What that's going to create is it's going to create this variable called LL that holds a variable called head. And what head does is it points to the front of the list. So when I first created a list, that list is empty. There's nothing in the list. Okay? Now, if I were to, so the idea for our array adapter example here would be, initially we have no credit cards. We have no loyalty programs. So we have a linked list with 0 elements in it. Therefore, when we go to show those things, it shows 0 things. Make sense? But now I want to add something to my list. So maybe I want to do a ll.add a 7. Okay? So I'm going to just make up a memory address here. I'll say 412. This will be a 7 here. I'll take the 0 off right now just so it doesn't, well, actually, let me leave it on just for visual sake. All right, so when I add this to the list, it will make head point to the first element in the list. Okay, and this guy, we're going to call this guy a node. We'll build a node here in a few minutes. Now, I'm going to add another guy to the list. So just to make this explicit, we're going to say add end. We're adding these to the end of the list. So we're going to add an end 5. So we're going to have a brand new node that gets created here. And this is going to be at 601 memory address. And here's our 5, and we're going to visualize this as being bucket 1 of our linked list. So the node that lives at bucket 0 knows the next guy in the list. We're bucket 1. So how do I get to the front of the list? I use my linked list, which has a pointer called head, which points to the very first element of the list. That guy then knows how to get to the second element of the list. That second element of the list is currently the last element of the list. How do we know he's the last element of the list? Because he points nowhere. The next guy in the list from his perspective is nobody. So that's the end of the list. That make sense? All right. So if this is a memory address and this is a memory address, these guys are not right next to each other in memory, right? I've made up some memory things, but linked lists do not require contiguous memory, right? They don't have to live right next to each other. Now that comes with a cost. So first of all, we're going to say they are memory efficient. That is to say that they can just be strewn all about memory. You can build your small house and then add a deck on later without burning down the house and rebuilding it, right? You can just add a deck, no problem. Deck might be down the street, but you can have your deck, all right? But linked lists are relatively slow. So they are memory efficient, but they are relatively slow. And the reason for that is when we looked at arrays, if I wanted to get to bucket 2 of that array, I could calculate exactly where in memory bucket 2 lived.
Just you need to know what the starting block is.
As long as you knew the beginning of it, right? With linked lists, you can't do that because things are not an offset off the base address. Instead, if I want to get to bucket 1 of my linked list, I go to the beginning of the linked list, I go to bucket 0, ask bucket 0, who's your neighbor? Follow that link to bucket 1. I can't just go from the beginning of the linked list to bucket 1. I have to traverse the list from the beginning. If I need to go to bucket 600, you start at the beginning, go to bucket 0, then you go to bucket 1, then you go to bucket 2, then you go to bucket 3, eventually getting to bucket 600 because you can't calculate the location of bucket 600.
So you have to traverse the whole list each time?
Yep.
Okay.
Relatively slow. That's the idea there. Okay? So we're going to build one of these. Go ahead.
I was just going to say, so is it easier to add in things on a list then? Or
Is it easier who what?
Like to add things in specific spots on a list or an array?
Well, it depends what you mean by easier.
I guess like you said, so with like a list, you have to go through each head point, right?
Yeah, I think the real answer to your question is this. If you're using the built-in linked list class that already has adds and gets and all those things, then it's just as easy because it's already written.
Okay.
Unfortunately, you can't use that class. You're going to have to write your own. So if you want to write add at index, you're going to have to write add at index. The good news is for our current assignment, we won't have to do that. Current assignment is everything's just always going to add to the end.
Okay.
And then we're getting an element at a certain position. Okay? But I'm going to actually write that linked list for you. Okay, I'm going to write a generic linked list for you. And then you'll have to adapt it for credit cards and loyalty programs, and then adapt our custom array adapter to show custom rows for a linked list of credit cards and a linked list of loyalty programs. Okay? So, I'm going to show you. Sounds easy, right?
Sure.
It's a piece of cake. All right, so.
I know it's not, but it sounds easy.
It actually is easy, but you're going to hate it. Your next week's going to be a nightmare, just a living nightmare. Yes, this is great. All right. Take good notes. Take good notes. All right. So our linked list class, in this guy, we're going to have a node called head. What's a node? A node, in our world right now, I'm going to create a linked list of integers. Okay? We're going to have a int payload. For your homework, so I'll just put a little note here. You might have a credit card called payload or a loyalty program called payload. The value that a node in your list holds a credit card or a loyalty program. The example one I'm building here is going to hold an int. So I'm kind of building this guy where I have a linked list of ints, where you might have a linked list of credit card here, credit card there, another linked list that knows how to hold loyalty programs.
And we're saying a credit card, it's holding the string of the credit card?
Whole credit card object.
Okay, the whole object.
Yep. Yep. And I'll give you a little hint. I'll give you a hint, so you'll still probably cry yourself to sleep, but it won't be as bad. All right. So my generic node here is going to be an int payload. And then I need to know node, next node. Every node needs to know where the next node is. Okay? So I'm going to come into my code here. Okay, now I'm going to write it here so nobody complains later. You cannot use the built-in data structures like linked list, array list, list vectors. Anything that you Google that you didn't write yourself, you can't use. All right? You can find plenty of documentation out there for like data structure classes and things like that that will help explain linked lists. But everything you're going to need, I'm about to show you. Okay? And I'm going to squeeze it into 15 minutes. So it's not that much. It's not that much data. Okay? The other hint is draw lots and lots and lots of pictures. Because when you're creating linked lists, when you hook something up, and we'll get to this in a second, when I add a new one of these here, okay, so I want to add a 6 to the end. What do I need to do? I need to traverse my list to get to the guy who's currently at the end, and then I make his next pointer point to my new dude. Okay, so I have to walk through memory in order to make this work, which sounds intimidating, but it's actually not bad. But I promise you'll find it intimidating, okay, because you're not used to looking at memory. All right, so where am I? So I'm going to create a new class here. I'm going to create node first. This guy's going to be a plain Jane Java class, so pretty similar to our credit card or our loyalty program. And I'm going to call this guy a node. Call them whatever you want, but I'm going to call it a node. Okay. Now, if you remember, credit cards have a whole bunch of things in them, right? So credit card keeps track of 4 different pieces of information. Loyalty program keeps track of 3 different pieces of information. A node's only going to keep track of 2 pieces of information. A node is going to have a private int, in my example, payload, and then we're going to have a private node next node, like that, okay? For your homework, private credit card payload or private loyalty program payload. Make sense? You're holding a different kind of value, different kind of payload. My guy's holding integers. Your linked lists are going to hold either credit cards or loyalty programs. Loyalty.
So can the payload literally hold anything? Or?
It could hold whatever you design it to hold.
Oh.
Okay, so you're probably going to have to write a credit card node and a loyalty node. Okay, and then next week I'll show you a better way of doing it. But don't overthink it the first time around. So I'm creating a node which my default node holds ints. Okay, I'll have my constructor for this guy. So public node. This guy will take in an int payload. We'll say this dot payload is equal to whatever that payload was. We'll say this dot next node is equal to null. When a node first comes into existence, it's here and it points nowhere. Okay, but it has a value. So when if I'm creating an instance of node here, this guy I just wrote, if I'm going to create this guy, I might say node n is equal to new node. Would I put a 6 in that one? And what that's going to create for me is this guy. That is a node whose payload is 6, whose next node points nowhere. Okay? This guy's going to have a memory address. That's going to be whatever this value is. We don't need to worry about that. And he's going to be positioned somewhere in my list. We don't keep track of the index, but that's where he lives. Okay? So when I first create a node, he looks like this. I then need to have the ability of setting this guy's next node to another node. Okay? I need to give myself that ability because in a little bit, I'm going to want to set this particular node's next node equal to n to keep that linked list going. Make sense? Okay. So this is what my generic node looks like. Now I'm going to come in here and I'm going to create a new Java class linked list. Okay, and a linked list has a single node called head. This guy points to the front of the list. So we'll have a private node head. We'll say always points to the front of the list. So when we first create a linked list, public linked list takes no parameters. We'll say this dot head is equal to null. That's the empty list. The empty list is a list with a variable called head of type node that points nowhere. That's a list with nothing in it. Make sense? So if I were to give myself a public void display to teach a linked list how to display itself, I'd ask the question if this dot head is equal to null, then system.out.println empty list, something like that. There's nothing in there. Else, traverse the list and display it. All right. Now, we don't currently have a way of getting things into our list. We need to be able to add things to the end of our list. Now, generally speaking, when we talk about linked lists, we're thinking about adding things to the front, adding things to the end, adding things to the middle. But if we're talking about building up a collection of objects, we really only need to be able to add things to the end and then be able to get things from a particular bucket, right? In order to solve our current problem, we're not removing stuff or anything at this point, so we really need kind of a cut down version of a linked list. So I'm going to need a function here, public void add end, and this guy will take an int payload as a parameter. Okay, this guy's job is to add this to the end of the linked list. So any way you cut it, I'm going to have to build a new node with that payload. Okay, so I have my node end, new node, payload. So what I just built there is equivalent to like this dude right here. Okay, Oh, but whatever. This is a node. This is a node. This is a node. These are all nodes. They're just in various states of their next node being pointed to things. But a generic one has his next node pointing to null, because that's what the constructor for node says. If I go back in here, the constructor here for node says when a node is first born, his next node points to null. Okay? So, for adding to the end, we'll ask the question. If this dot head is equal to null, that is, if we have the empty list, then what will we do? We'll say this dot head is equal to n. We're done. We just added it. If you have an empty list, adding something to the end of that list says make head point at that guy. Right? Else, not the empty list. That means I have at least one element. So I need to walk my list until I get to the guy who's currently at the end of the list. And who is that guy? The guy who's currently at the end of the list is the node whose next node is equal to null. If I look at this picture here, this is what my list currently looks like. Head points somewhere, right? So I'm in the else. Does this guy's next node point to null? Nope, he points to a real place. So I need to jump here. Does this guy's next node point to null? Nope, he points to a real place. So I have to jump here. Does this guy's next node point to null? Yes. He's the end of my list. So what do? I set this guy's next node to the node I just built. So I need to walk to the end of the list. And I do that by creating a temporary node pointer, maybe called kernode. And we'll start this off at head. So we'll start off at the beginning of the list. And then as long as kernode's next node is not equal to null, I need to jump to the next node. I need to hop from node to node to node until I finally land on a node whose next node points nowhere. That's the end of the list. Okay? So I want to say here, while kernode dot, I want to say get next node. But the problem I have right now is inside of node, my next node is private. But good thing, we have our generate getters. So I'll go ahead and generate. I'll get it for next node and payload. So we can get both of those guys. So now I have the ability to get a payload. I have ability to get the next node. Come back in here. So I'm asking the question, while kernode dot get next node is not equal to null. If it points to a real place, then I want kernode to equal kernode dot get next node. Jump to the next guy in the list. I'm using kernode here because I don't want to change head. Head always needs to point to the front of the list. Okay, so what I'm using is I start kernode pointing to the same thing head points to. He's like, are you the end of the list? Nope. Are you the end of the list? Nope. Are you the end of the list? Nope. Till you finally get to the place, whoa, we're at the end of the list. I'm going to point to the new guy. Okay, so that's what this little while loop here does. He will keep updating kernode to be equal to his own next node until he finally gets to a place where his own next node points nowhere. So when I'm here, I am at the end of the list. So I will say kernode dot, I want to set kernode's next node equal to n, the node I just built. But I need to have a setter for that. So I'll go into here. I'll right click, hit generate. I want to generate a setter for next node. I don't want to be able to set the payload. I just want to be able to set the next node. So now I can set that value because that guy's private, so I can't set him directly. So I need this public method to set it. So I'll say kernode dot set next node to n. and that will add that guy to the end of the list. Make sense? Now, I'll do one other thing here that might help you. I'm going to say private int count. This dot count is equal to 0. Whenever we add something, we will say this dot count plus plus. A new thing has been added to the list. This will allow us to ask questions like, how many elements are in my linked list? So just like we can ask a string what its length is, and we can ask an array what its length is, we can ask a linked list what its length is. I could have named the method whatever I wanted, but just to match up to strings and arrays, the length of a linked list is the current value of its count variable. Its count variable starts off at 0 and goes up every single time we add something. Whether I added it here or I added it here, the count will always have 1 added to it. Okay? Now I want to show get. So public, I'm going to have it return an int right now. We're going to have this guy called get at index. Okay, now as a hint, you might have a public credit card get at index, as well as a public loyalty program, whatever. My linked list holds integers. Yours holds credit cards, and a second one might hold loyalty programs. All right? So get at index. We're going to go ahead and assume for this exercise that the index you pass this is always a legitimate index, something between 0 and count minus 1. Okay? So I want to return the payload that lives at a particular node. So I want to go through here and I want to say something like node cur node is equal to this dot head. Okay. Now I want to jump to index index. So for int I is equal to 0, I is less than index, I plus plus, cur node is equal to cur node dot get next node. So this will zip cur node down the list until he finally lands at node index, and then I'll return cur node dot get payload. I'm not removing or anything, I'm just giving you the value that lives at that part of the list. Okay? You're going to probably need that portion of it when you do your custom get view that says, get me the view, get me the credit card from bucket 7 of your linked list. You'll ask your linked list to get at index 7. Okay? So that's my linked list. So let me show it to you work real quick. So just inside of main activity. But you don't think that's enough? All right, so I'm going to say I'm going to have a linked list called LL. That's going to be a new linked list. And then I'll do for int I is equal to 0, I is less than 10, I plus plus. And we'll say ll.add end I. All right, so that should add a bunch of stuff. And then I'll just write another loop here that says for int I is equal to 0, I is less than ll.length, I plus plus, system.out.println, and I'll just so we can differentiate and know that this is part of our linked list, I'll say ll.get at index I. All right, so now when I run this, let me open up logcat here and just delete all this crap. This is just going to be out here at the command line. So there's my linked list, 0 through 9.
No freaking way. I'm so screwed.
I'm only 3 minutes late.
I know.
You asked a question. You threw me off.
Yeah, it's true.
Now, what'll make this all worse is
I'm excited.
the amount of time you're going to spend on this assignment is going to destroy your soul.
Yeah.
Okay?
Yeah, it is.
And then we're going to come to class next week, and I'm going to solve it in like 10 minutes. I'll go slower than that, but I had to run. You're going to want to rewatch like this last 15 minutes of class. I had to go pretty quick, but my advice would be really focus on understanding what we did this last 15 minutes. We've reinvented an array. We've built our own array that grows dynamically. Okay? It starts off with a count of 0, then 1, then 2, then 3, then 4, because I just keep adding to the end of it, right? And I have the ability to get stuff from it as well. So whenever I add a new credit card or I add a new loyalty program, I'll say core.linkedlistofcreditcards.addEnd, CC. core.linkedlistofloyaltyprograms.addEnd, LP, whatever I call that variable. So that'll just keep adding stuff to my linked list. Then you're going to have your custom array adapter that instead of taking an integer array or instead of taking a credit card array or a loyalty program array, it'll take in a linked list of credit cards that you'll have to write, and the other one will take in a linked list of loyalty programs that you'll have to write. Those guys will be extremely similar to each other, except for the fact that the payload for a node holds either credit cards or loyalty programs. I would recommend that you write it as don't try to get fancy. Write it as 2 completely separate objects. Have a linked list of credit cards with a credit card node, and have a linked list of, and then have a linked list of loyalty programs, and have the nodes for that called loyalty nodes or something like that. Okay? Model it after my linked list of integers. All right, so for next week, you're going to accomplish what we did in part B, part 2 of today, where we wrote our custom array adapter. And I've already done that for credit cards. That's what we did for credit cards, right? So do it for loyalty programs as well. So maybe convert your program first to that, the array version. Then upgrade that to the linked list version so that you no longer have to fill it up with 1,000 pre-things. Make sense?
Makes sense.
All right. So I ask for bribes now or midweek? Midweek bribes. All right, I will push this code so you will have it.
You take prenatal vitamins?
I do.
Very well. Boy or girl?
Why?
Yeah, he's a cute little guy.
Thank you.
So, yeah, you can get that. It's hard. You don't understand what I'm saying, but you do very well.
I would strongly recommend that you guys get together as a group and maybe work on this. I would strongly recommend that, John. Maybe put together a study group for this one and get together with 3 or 4 of you and work on it.
Yeah, be good.
This is a really good assignment for learning, but it's going to be challenging.
13 months now.
Yeah, I guess like, yeah, we'll have to.
They're very energetic. You guys know your
We
type.
can try.
I mean, you could even do something with like Google Hangouts or whatever. You don't have to come together in the same location. Just yeah. So I mean, the bigger problem is maybe schedules and stuff, but figure something out. It'll make all of your lives easier, probably.